that's what those next two talks are on. So right now we have Rachel in from UW, my favorite collaborator as well. So she's going to attribute-based encryption from LWE and its recent cousins.
Unlike you usually think about homomorphic computation with respect to homomorphic encryption, I'm going to talk about homomorphic computation in several new and interesting primitives. They talk about homomorphism in a different way. And my focus is to try to show that we can do restricted kinds of homomorphic computation you would like. You just evaluate any kind of circuit you want. And get really succinct, very small size primitives. So that's like an additional bonus. And they joined to work with my student Yaqin at UW and Zero, who's going to Boston for postdoc. All right, so we have, as I say, lots of different homomorphic primitives. Most familiar may be homomorphic encryption, but I would just cast what's homomorphic primitive. It's something that involves secrets, but we're not satisfied with just hiding secrets, preventing tampering of the secrets. We also want to do computation of the secrets. So I think the supports computation that involves secrets in interactive and reusable or succinct way accounted as a homomorphic primitive. If you allow interaction, then there are a lot more solutions. And if you don't care about succinctness, there are also a lot more solutions. So I think and homomorphic encryption in this broad umbrella also puts functional encryption and indistinguishability obfuscation. And so another concept which is going to be the focus of today's talk, which is called attribute-based encryption, which I will tell you very soon. And more, since I'm not going to touch them, so I won't tell you about what they are. Homomorphic primitive, what do I care? Is I can do any computation I want, right? So that would mean for us circuits. And if I want efficiency, a lot of those are encryption schemes. So therefore, I want the components like ciphertexts and signatures to be as small as possible. I want weak assumptions, right? So these are the usual general goals. So the big we all know is in this domain is the dimension of homomorphic encryption, right? So here we care about privacy of an input X. So we write it as kind of inside a box with a keypad. I can get privacy, but also allow you to evaluate some function under the hood inside the ciphertext without actually decrypting it. So you can move from encryption of X to encryption of f of X, what you want. So here the expressiveness really means that I can evaluate any polynomial-sized circuits I want on an encrypted input. So what does this mean? Public key ciphertext to be as small as possible. And what we can generally achieve is more or less the best you would expect, which is polynomial-size public key and the polynomial-size ciphertext, where it's also linear dependency on the input size. So in fact, we can do better. We can do ciphertext, which is the same as the input size, plus some polynomial factor, not multiply. But for the purpose of this talk, the polynomial factor in the security parameter is just for free. So I won't differentiate. Yes, you can, yeah. One glitch, which we often just ignore it, is that the assumption is what we call circular learning with errors, which I will tell you very soon, which is more or less the learning with error or gaps learning with error, but slightly stronger. If you don't want this circular adjective, we will end up with a slightly weaker primitive. Of the computation you would ever want to compute. Right? Maybe in some cases you only want to do matrix multiplication, and the steps is going to be, some logarithmic value, therefore you're willing to commit it ahead of time. But it's undesirable. And just claim the only computation I ever carried out will have 2 to the 128 steps. So I just put 2 to the 128 in the setup algorithm. They pay for it. This 2 to the 128 that they generate, and the ciphertexts are all going to scale with that. So just an arbitrary upper bound isn't going to work. We can base it on the plain learning with errors assumption. So those two assumptions is going to also be an interesting point for the algorithmic people. Learning with error says that if I give you matrix A and a lot of noisy linear evaluation with respect to a secret S, however, you don't get directly the output, you get output perturbed by some small noise in the sense that the L infinity norm of this noise vector is small. And we are operating over large fields. So really, you're thinking about it's almost like a linear evaluation, and in a very large field, I just kind of added a little bit low order bit noise, right? Now the point is that the learning with says these noisy linear evaluations, in fact, look pseudo-random. Okay? We can't differentiate this noisy linear evaluation away from random strings. What is error? Linear evaluation depends on function output that depends on the secret itself. That's what the circular part is. It's not strange to say we're going to use the noisy linear evaluation to hide a fixed message, because that's more or less how we would use it, because it's pseudo-random, you can't tell apart from random, so it's a very good hiding tool to hide a fixed message. But okay, that's called circular assumption. What do we know about it? We know relatively little. We know for LWE, this function is linear, more or less. For a lot of linear functions, we can prove it's the same as LWE. However, we talked about in the previous slide where I can evaluate arbitrary polynomial-size circuits, linear circular assumption is good enough. In fact, you're going to encrypt a function on the secret, depending on the secret, that's quadratic. And the fact that we don't know if it's the same as LWE or not. Assumption by now is used in the literature quite a lot, and we haven't falsified.
4 years older than again.
Variant of LWE, we have more variant of LWE as you see towards the talk. Yeah. And it's lots of applications. It's not the only homomorphism that we care about. We can think about computation with secrets in a myriad of different ways. So one primitive for the attribute-based encryption is very interesting, but perhaps lesser known. Okay? So what attribute-based encryption? It's enhancement of encryption, meaning that I hide a message mu inside my ciphertext. But text is also tagged with an input X, which we sometimes call it attribute. That's why it has the name attribute-based, right? So I'm encrypting different messages, but every time when I encrypt, I tag it with some input X. can view them as attributes for this ciphertext. What do I use these attributes for? You can actually use the decryption key. This using, we call the master secret key. But it is a function f. And here of ciphertext. What type? Those attribute x by this function f. So like a cryptographic way of doing access control, where we're not doing access control using machine enforced policy enforcement. We're doing access control using mathematics, where if someone holds only the secret key for function f, the is function f, right? Of thinking about homomorphic computation, and in fact, how do I think about homomorphic computation? The reality how to do such a thing during the decryption procedure, what usually is that one can start with the original ciphertext, use homomorphic computation, ciphertext for the same message mu, with the output f of x. So first we do attribute x. That's homomorphic encryption. Because I really don't care about privacy for this x. This x is something in the public. The decryption algorithm will know it. What I care about is the correctness of the computation. I want to know that it is impossible for someone to get a ciphertext of mu that is tagged by f, the opposite of f of x, right? To flip the output computation. So you can use like the signature analog of homomorphic computation, where I don't care about privacy, but I care about integrity of the computation.
So wait, what are you considering the computation to be here? Is it on the attribute itself, or?
Computation of the attribute itself, yeah. So the computation happens on the public attribute, and the security is that if the output is 1, for example, you're supposed to decrypt. If the output is 0, then you can decrypt. Homomorphic computation. Maximal depth you want, and after that, you can evaluate, you can generate keys for those functions that have that depth, up to that depth. And every component in your system is going to pay polynomial in the depth factor in their size. This is really of level of homomorphic encryption, and it uses LWE. Makes sense. Like, all right. What if I'm willing to pay more? What if I'm willing to use circular LWE? Other things. Unbounded version, where I don't have to restrict the depth of the computation, and my ciphertext and public key don't have to pay for the depth of computation. This turns out to be open for a while. And in fact, if I look back in this of homomorphic primitives, there are 2 more primitives that we don't know how to support unbounded depth computation. They suffer from similar drawback, that they can only handle bounded depths, and their size efficiency is going to degrade with polynomial indeed. So the question is, can I do this unbounded depth homomorphic computation with integrity of computation? It seems like integrity is the changing game here, what separates this primitive from homomorphic encryption. Yeah.
What about this last or first column here?
Yeah, very good question. So I do know that homomorphic commitment you can do unbounded depths, and then I was told that Constraint PRF, my student looked at. I don't know if there are results written. My student looked at it and said that it should be okay, based on prior techniques, which I haven't verified. Homomorphic signature, David told me that there's some other paper that implicitly solved the problem, but I don't think it was explicitly.
I think there's an upcoming crypto paper that makes sense.
Okay,
Yeah,
cool.
so let's vote for it. Give me five. Oh, give me five. Oh, this password. Yeah, remember the password.
And told me that he thinks it just follows from prior work. I don't know if it's correct.
I follow. That's because of the universal circuit. So I think you can do unbounded depth, but the universal circuit, I think.
Possible, yeah, I haven't talked to him. So. Okay. Does that answer your question? So it seems this is still questionable, but the other also, yeah. All right, so actually, I won't tell you about reusable garbling, or tell you about the laconic function encryption, which is by itself an extremely interesting primitive, I think. So, secure application has a function f, Bob has input x, and x is the sole person, we sometimes call it the receiver, who receive an output through this computation. What they should receive is f evaluated on x, right? And the point is that Alice and Bob are uncomfortable with sharing f and x in the clear. And that's why they need to do something cryptographic. And there are many ways to achieve this. For example, using the classical garbling scheme plus oblivious transfer. There are different techniques for multivariate computation that can be used here. The general drawback is that we, for many years, believed that this secure exchange of information evaluating a function requires a lot of communication and computation. In particular, both parties were paid for the runtime of the function f, and they will have to communicate the runtime of the function, the runtime number of bits at least, right? What about doing something better? So if you still remember Daniel's talk, homomorphic encryption gives us a much better way of doing such things, where x could encrypt your function f, which may have very succinct description. For example, maybe function f is to say access index I in the database X, right? It has a very short description. Using the homomorphic computation, an encrypted output, right? And then Alice just need to decrypt. Size of the function plus the size of the output. And depending on whether you have the full homomorphic encryption or not, there will be an additional polynomial factor in the depth D. One person has to pay, which makes sense. If Bob is the server and Alice is a client retrieving one point in the memory X, then it makes sense that Alice only do small computation. What if we want to flip the table? What if I want Alice, the receiver, the one who pays, to be the one who is efficient? Makes sense, right? Bob is a user holding his own private DNA, and Alice is the server who is collecting some private information about other different clients' DNA. Benefits out of this output, so Alice should pay. So I wish know how to achieve using fully homomorphic encryption. So we have a laconic function evaluation. So here the X is going to send a public key depending on the function f. And Boneh is going to simply encrypt this input x he has. And if the public key to be efficient, the public key of f should be almost like a digest of this function f. You can think about it as a hash of this function f. So just depends on the size of Bob's input and the digester size, which is something security parameter. Now with FOCS. So this is called laconic function evaluation. And here we have this separation between bounded versus unbounded version comes up. In the bounded version, that the communication is going to be smaller than the runtime of the computation, but it scales with the depth of the computation. The bounded version, we would like to get rid of it completely, right? Okay, so hopefully it convinces you that these homomorphic primitives that care a lot about integrity of the computation are very, very interesting. And we didn't know how to support unbounded depth computation without using heavy hammer like indistinguishability or obfuscation. Hopefully it's be much closer to homomorphic encryption itself. So it's strange that I cannot just duplicate the same result using circular LWE. So this is what we do in this work. We show that the first two primitives can be constructed using circular LWE with unbounded depth. And the second, we don't quite get there. We still need a stronger assumption called evasive LWE. Okay. So
this question about circular LWE, is there like a single version of what circular LWE is? Like a single canonical version?
There's one version that applies. I don't know if that's enough for you. I mean, it's enough for all the efficiency.
bottleneck, what separates the case of integrity from the privacy, and then give you a little bit idea about what's our technique. So, all right, what's the main issue? Let's go back to how we generally do homomorphic computation. We have a very limited technical arsenal. That we have some encoding based on those noisy linear equation LWE assumption. Those encodings are, as you can imagine, they're hide information on use hide or bind information using some noise because it's look like S times A plus E plus X. This is a very typical structure. So you see some noise in those encodings. We have to live with. On one hand, it makes things secure. Encodings. The noise would accumulate. Because I don't have any signal of the encoded value anymore, right? So towards going to unbounded depth evaluation, noise management, right? Somewhere when it becomes too large, I need to have a very good way of reducing the noise and keeping the same encoded value. So this is called noise reduction, and in the space of homomorphic encryption, it's called bootstrapping. That I just infinitely loop through the things and then I can keep evaluating. context of homomorphic encryption, when we have a noise that encodes Y, this may be coming out of some intermediate computation, it has too much noise. How to reduce the noise? Well, one way to reduce the noise is this up, like noise in encoding, or it and then remove the noise once right? Homomorphic way by itself. So let's have encoding of the secret key itself, right? And once I evaluated on the secret key, I'm going to evaluate this function G. Use secret key of ciphertext I want to refresh. So G is now viewed as a function on the secret key, and you can of the description of the function G, right? It's baked into the circuit G. Evaluating homomorphically on the secret key gives me an encoding of output Y, and depth algorithm. It's usually just NC1 logarithmic depth. Therefore, not sort of level like logarithmic level evaluation. So it's not too big. And has from here to here, I have achieved my noise reduction. Okay, so method. As an observation, this is where the circular algorithm comes in because you have an encoding of the secret key itself. So once I do the same thing when I care about integrity of the computation, so how we can enforce integrity. And it turns out that FHE way is not going to work because if you have a FHE encoding of input X, you can evaluate f of X, you can evaluate f prime of X. To tell like f prime X of X, which one is like evaluating the right function or not. So what we still homomorphically evaluated to f of X, but for X is known, this is going to create problem. We're not trying to hide it. Moving the computation now, I am in fact also moving the public key associated with these encodings. So if my original encoding is with respect to one public key, my encoding is going to be with respect to another public key. Now there is a way, the function you're evaluating. It's a way for me to say the right output or the right output or the wrong output. So if we want that the output ciphertext, if it's valid with respect to the new public key for F, this attribute has to be f of X. It cannot be the opposite. Know how to say what it means for an output ciphertext to be restricted. On the input X and on the public key, I want it to be independent of the X itself and also independent of any encoding randomness. This is natural because you don't want the key to depend on the ciphertext, right? Because otherwise, what kind of key is that? It means it can only work for one ciphertext instead of for multiple ciphertexts. So on the secret key, of whatever ciphertext that it might later attempt to decrypt. So bootstrapping would not work in this setting. Let's try. Say that I have an encoding now with lots of noise, and I call this encoding C. Okay, I'm going to start with an encoding of the secret S. And let's evaluate the decryption algorithm that is going to decrypt this ciphertext C. And attribute f of x, because that's the right output. One problem, which is this homomorphic computation requires knowing the attribute as in the cooler. If I know the secret in the cooler, it's not good. Going to correspond to as a public key. That's the public key for the encryption circuit, right? Ciphertext, right? Because the whole point about bootstrapping is I bake this ciphertext that I want to decrypt the circuit that I homomorphically evaluate. For one ciphertext instead of for many, and that's not good enough. All right, so this is why bootstrapping does not work. So I think I have 10 minutes. Do I have 10 minutes? Yeah. I give myself 10 minutes. I learned from the brilliant mind. The project. For the BGG plus 14. On the WE. If I have an attribute X, I can code it bit by bit as usual. And how I take a matrix AI and I shift it by xi times g, and I'm doing LWE, right? Use that as the matrix in LWE and give an LWE sample for that matrix. That's it. So won't tell you how this is done, but just know this could be done, that there's the dual homomorphism on the public key and on the ciphertext, which moves this matrix A to some new matrix AF, and move this encoding of X into an encoding of the output Y equals to f of X under this new matrix A. Okay? So you see that computation happened both in the Y part and the matrix part. And furthermore, the new matrix can be computed from the previous matrix and the function f alone. So now here, if we did the previous bootstrapping, I'm going to end up with a matrix that depends on something specific of the ciphertext. For the rest of the talk, for me to think about this encoding, I use a random path, which is just a plain LWE sample with respect to AI. The payload, which is x times g. For cryptography, S as an authentication key, which is authenticating the correctness of the computation outcome, and it just happens to share it with LWE sample. So for us, this is encoding that is used in AB, laconic function evaluation, reusable garbling. We give a noise reduction procedure for this encoding. And the two key points is I want to start from large noise to become small noise while making sure that the new matrix is input independent. All right, so how do we do that? We have a step approach. In this step, we're going to completely remove this large noise. And we were with encoding, however, that is where the payload, the right payload is hidden by some depend on the secret, which makes sense. It's not gonna be the right format. Okay, so means that if I act with this, computation. We're going to evaluate separately this function on the secret S in the right format. So once we can do both steps, we add them together. This ill-formatted one-time path is going to cancel out, and I will get the right outcome.
point is that this function that you're computing on the right is independent of the secret and ciphertext also.
Precisely, yeah. The key point is that this function on the x, this function pad, is really just a fixed function. Right? It has nothing to do with what is y, what is e, what is s. Yeah. Okay, so like there's some formatting issue. Okay. I sent it to my phone and then sent it to my iPad, and maybe something happened during the way. Okay. So that's what I'm gonna correct it, their running size. I want to remove the noise inside a sample. How do I do that? The rounding seems to be the technique to go. So let's try it. So if I round it, so here I have mod q, then in the rounding I can take out the mod q by modding q over delta. Now I have rounding of some sum of 3 terms. You can always separately round them. Yeah. You can always sum into some of the roundings with a little bit of the noise. That happens using a kind of a trick that if I have a term which is s times a rounded by delta, and if s happens to be small, if you think about s is just value 1, then you can simply take s out. If s is small, then you can take s out, but it incurs some small noise. So it goes to 0 as long as I'm rounding by a value that is larger than the noise. Okay, so why not put enough? There's reasons. If it's like S times a matrix, what's the noise? Y times this term, right? This point, but actually it is okay because factor happens to be able to divide this matrix G, which I haven't told you about. This is called the gadget matrix. It contains a lot of powers of 2. So if my rounding factor delta happens to divide this matrix G, then basically S times G, which is containing small powers of 2. So it looks like a good format. The real problem is that in the procedure, I am using modulus, right? I have 1 from modulus Q to modulus Q divided by delta. Here, like modulus left. My modulus is 0 and I'm done. So that's why is usually associated with bounded depth evaluation instead of unbounded depth evaluation. So during I can recover the modulus. I can run to noise small, noise modulus back. It is not clear how to do because if I just multiply by 2 to the k, a delta, I will back noise again, right? Because there is noise and then I multiply by 2 to the k. So I don't have to do rounding without losing the modulus. Without any noise. What if my rounding result doesn't have any noise? Then I can go back, right? Noise removal, rounding without any noise left. Gadget matrix, which I told you consists of powers of 2. I'm going to look at them as one contains small powers of 2, part that contains large powers of 2. And we will separately handle them. And this will give us the right payload. But then the methods for dealing with small powers of 2 and large powers of 2 are different. So we're starting with the larger powers of 2. So give me a large encoding, or take the parts which contains large powers of 2. What do? I round it by 2 to the k. What happens? What happens is, well, I have here a mod q, which means there is some term of some multiples of q. Then I have large powers of 2. So if I is a multiple of the rounding factor, then it just produces the outcome. So what I have is this one. Round up to j, means that s times a prime is within the region of some multiple times 2 to the k to the next multiple times 2 to the k. What would be a region where this plus noise is going to go to a different rounding result? Hence, if the value is very close to the boundary of the rounding, right? If it's very close to, and you perturb it by some noise, it goes into the next region and it will round to j plus 1 instead of j. Negligible probability, my s times a, the value itself is random. Just get rid of the noise. So, noise, I'm going to multiply with 2 to the k to recover my modulus. What happens is I will end up with the g large again, and this multiple of q is simply 0 when I'm on q. And this is my new pad for the payload. And you can also observe that this is not a well-formed pad. It doesn't look anything like s times a plus e. Okay, so we have a separate procedure for generating the small part of the payload.
So it sort of does look like a good, right?
It sort of looks like a good pad.
Yeah. S is small, then it's roughly, S transpose a rounded A prime plus an error.
Yeah, but once you're gonna have p round plus 2 times 2 to the k. Right? That's a part that you cannot recover the modulus and then still have the well-formatted. So I won't tell you about how do we generate the remove the noise for the small powers of 2 in the G term. It uses a different procedure, but a kind of a similar flavor. So suppose now that I have managed to come to an encoding of y times s times g. So now a function that looks like some SA divided by delta times delta, something like this, right? How to go back to a well-formed BGG encoding so that I can continue evaluation? The goal is I want to have BGG encoding of the pad itself, right? And is a fixed function, right? The pad function on input s is a fixed function. And of y independent of the noise or those ciphertext sensitive information. How do we do that? Well, let's think just starting from BGG encoding of secret s, and I want to evaluate the pad function on it, so do it. The first part knowing s in the clear. That's already been solved by prior work. One solution is of the FH encryption of the secret s. So I evaluate basically the pad function of the secret s instead of s itself. with the FHE encoding, FHE ciphertext. Encryption itself. It's almost like coincidence. Indeed, ciphertext for many FHE encryption schemes is simply decryption procedure. We produce the output with some FHE noise. And with that, we basically get the path and encoding of the path. Okay, so this basically gives me the full thing. Now, this procedure allows me to reduce the BGP encoding noise whenever it becomes too large. And therefore, I can keep evaluating. No matter how deep the function f is, I will eventually get an encoding of the output for AF. Am I out of time? Yeah.
Yeah, you could wrap up.
Okay, so I will wrap up. So with this procedure, I basically already have laconic function evaluation and the reusable double circuits. However, we don't really know how to get AB directly. The main problem is that when of doing AB, which is I just encoded the attribute X using this encoding, and what they will allow me to do is to get the encoding of the output under the public key AF. Because the encoding is unknown at the encryption time, so in some sense I can also write message mu using another LWE sample with respect to some generic public matrix U. So in the usual case, AF to U, so this term goes away, I will be able to decrypt. So provide a small vector which satisfies essentially that AF times R, but concatenated with some independent matrix B is going to be equal to U. And what this allows me to do is that I can just collect those LWE samples I can get, multiply it with R, and this will give me essentially as U. In the case Y equals to 0, this goes away. And I can decrypt. The problem now I have this additional thing, like in the system, not only have LWE samples, no matter how complicated they are, I also solutions, small integer solutions of some matrix equation. And we don't quite know how to simulate these small vectors when using our unbounded depth evaluation. And the key point is that it is highly nonlinear. It performs these like rounding procedures. And when you have these nonlinear operations, we don't know how to simulate the R. And this is where that evasive LWE comes to help. It basically gives a way to reason about, a new way to reason about security when there are these small integer solutions. What it says is that when you can effectively use these small integer solutions is to multiply it with the LWE sample, which will give you some new LWE sample, a completely fresh LWE sample. Samples together, them are pseudo-random. If the samples themselves are pseudo-random, then the original samples is also pseudo-random, even at the presence of those small integer solutions. Short with evasive LWE is we no longer need to simulate these short integer solutions in the secret key. All what we need to do is to analyze jointly all the LWE samples that we have, what we can get using these small integer solutions. And that we can analyze essentially using the same technique as we saw before. All right, so that's it. One big question obviously is, can you get rid of this evasive LWE, which still doesn't seem to be the right answer. I really believe the right answer is using circular LWE.